Collision theory and rate changes for AQA GCSE Chemistry. I will set out collision theory, review reaction profiles, look at concentration, pressure and surface area effects on rate, temperature effects and catalysis. Chemical reactions involve a change from reactants to products. The rate of reaction could be counted as how fast the reactant is used up, or counted as how fast a chemical is formed, how fast the product is made. Collision theory is used to explain changes in how fast reactions occur, that is, changes in rate of reaction. For a reaction between two particles to occur, simple collision theory uses two main ideas. The first one is that particles must collide. The second one is that the collision must possess a minimum energy. Collisions that have that minimum energy and result in a reaction are termed successful. Collisions that do not result in a reaction are unsuccessful. An important point is that the vast majority of collisions are unsuccessful. A review of reaction profiles. If we consider reactant A and reactant B making a product C, on the reaction profile we have energy and course of reaction. A and B have an initial energy level as reactants, and product C has a different energy level. To go from A and B, the reactants, to the products, there is an energy barrier between the two. The height of that energy barrier, the difference between the initial energy of the reactants and the top of the reaction profile curve, is the activation energy. That is the minimum amount of energy required for a collision to be successful. If A and B possess the minimum energy, the activation energy, they can progress and form product C. Let's move on to consider how concentration and pressure changes and surface area changes affect rate of reaction. So let's consider the effects of increasing concentration on rate of reaction. In my diagram, I've got two types of particle, blue and black. They're in solution, so they're in a fixed volume at a fixed temperature, and they are moving randomly. You'll see that collisions occur, and these occur at a fixed frequency. If, however, the number of particles in the fixed volume is increased, so I've increased the blue particles and the black particles, then we can see that there's an increase in the collision frequency. That is, there's more collisions per second. Our conclusion is that an increase in concentration, that is, an increase in the numbers of particles in a fixed volume, leads to more collisions per second and therefore a higher rate of reaction. So here is a task for you. The explanation of higher concentrations producing higher rates of reaction is that could you link three ideas together to explain how higher concentrations lead to higher rates using collision theory? Pause, write your three statements, come back to check when you are ready. Okay, so I'm going to reveal my first statement. A higher concentration, first of all, means more particles per volume. So you need to explain what a higher concentration means. This results in more collisions per second, a higher collision frequency. Well, if there are more collisions per second, we achieve more successful collisions per second and a higher rate of reaction. Now, the arguments for slower rates of reaction with lower concentrations are simply a reverse of these arguments. So if we now consider the effects of changing gaseous pressure on rate of reaction, well, we'll start with blue and black particles as with concentration. They're moving randomly in a fixed volume at a fixed temperature. There is a fixed rate of collision, a fixed number of collisions per second. If we increase the number of particles in that volume, more blue and more black, then we will get more collisions per second. That is, there's an increase in the collision frequency. Now we call, in a gaseous system, increasing the numbers of particles in a fixed volume an increase in pressure. So we conclude from collision theory that an increase in pressure leads to an increase in collision frequency and therefore an increase in rate of reaction. So to summarize the effect of changing pressure on a gaseous system, please complete these 4 statements. A lower pressure means less, which results in therefore there are less effective collisions, needs to be completed. So a lower pressure results in again, complete the statement. Pause, complete the 4 statements, come back to check and correct when you are ready. Okay, so a lower pressure means less particles per volume, which results in a lower collision frequency. Therefore, there are less effective collisions per second, per minute, per unit time. So a lower pressure results in a lower rate of reaction. Let's apply collision theory to surface area effects. So we have here a particle in 2 dimensions. So I'm going to carry out the argument in 2 dimensions. And we're going to divide it into smaller particles. Now, if we do that, you'll see that I've got the same total volume, but I've increased the surface area in my 2-dimensional model by these surfaces here. These are additional. That is additional surface area compared to the particle on the left-hand side. So in 2 dimensions, we see that dividing a particle into 4 particles, keeping the volume the same, increases the surface area. That is, increases the surface area to volume ratio. Now, that effect is more marked in 3 dimensions. So there's a large increase in surface area compared to a fixed volume when you divide a large particle into smaller particles. So what does that mean for collision theory? Well, we have available a certain surface area on the left for collision with other reactant particles. Of course, there's a greater surface area available for the same volume for collision with other reactant particles when we've divided into smaller particles. So we are increasing the surface area available for collision with other reactant particles and therefore increasing the rate of reaction if we move from large particles to small particles. The terminology is there's an increase in the surface area to volume ratio. Of course, reverse arguments and effects apply to any ways of reducing surface area. So here is a problem for you to try, a typical exam question. Compare and explain the differing rate of reaction between small marble chips and dilute acid to that between the acid and the same mass of large marble chips. Generally, this would be worth about 3 marks. So come up with your answer. You'll need 3 logically sequenced statements to achieve the 3 marks. Pause, complete the answer, come back to check when you are ready. Okay, so here is my set of answers. First point is that the small marble chips will have a greater surface area to volume ratio than the large marble chips. Therefore, there are more collisions per second between the small chips and the acid than between the large chips and the acid. So more collisions per second. Therefore, the rate of reaction is greater for the small chips than for the large chips. Don't forget to write that statement. You're asked to compare and explain the differing rate. So you need a clear statement at the end of the difference in rate for the small chips compared to the large chips. So the explanations for the effect of concentration change, pressure change, surface area change on rate using collision theory focus on collision frequency. However, temperature effects and catalysis are more concerned with the energy of collision. So the effect of temperature change. Now, the principal effect of increasing temperature is to increase the movement energy of the particles. Of course, for a collision to be successful, that is to result in a reaction, the colliding particles must possess the activation energy, that is sufficient energy. Now, most collisions are unsuccessful. A very small proportion of the collisions that occur at a given temperature result in a reaction. The vast majority of collisions do not produce a product. But at higher temperatures, because the movement energy of the particles is increased, there's a much higher percentage or proportion of collisions that are successful, that result in a reaction. So increasing the temperature leads to an increase in the rate of reaction. How is this explained? Come up with 2 statements, 2 ideas that are linked. Write them down. Come back to check and correct when you are ready. Okay, so I'm going to reveal my linked ideas. There's an increase in the property of the particles as the temperature increases. That, of course, is the kinetic energy. If the kinetic energy of the particles is increased, so more of the collisions possess the activation energy and are successful. Note, raising the temperature also causes a small increase in collision frequency. The particles are moving faster. The reverse arguments, of course, apply to reducing temperature. Catalysts are added to a reaction in small quantities and they increase the rate of a reaction but are not used up in that reaction. So if we look at an energy profile here, a reaction profile, we've got our reactants and products. Here's our reaction profile curve. Here's the activation energy for the reaction, the difference between the energy state of the reactants and the top of that profile curve. Well, the theory, collision theory, says that catalysts provide a different reaction pathway with a lower activation energy. So here is the different reaction pathway in red, and here is the new catalyzed activation energy. It's much lower. So the energy requirement for reaction on collision is much lower. So many more particles at a fixed temperature possess or exceed the activation energy, and therefore there are many more successful collisions per second. Hence, catalysts increase the rate of reaction. Enzymes are biological catalysts. There is one instance of the use of a biological catalyst, an enzyme, in the chemistry specification, and that is the enzymes contained in yeast that catalyze the anaerobic, that is the oxygen-free fermentation of glucose. So here's the chemical equation for that fermentation. Glucose, 2 molecules of ethanol and a waste gas, carbon dioxide. Note, the catalyst or the enzyme does not appear in the chemical equation. If you recall, catalysts, enzymes are not changed by that chemical reaction. So they do not appear in the chemical equation. One difference between enzymes and catalysts such as transition metal compounds is that the enzyme action is slowed by temperatures above 35 degrees Celsius. So in this example, there's a temperature of 35 degrees Celsius above which the enzyme is less effective. Now I'll move on to trying some textbook questions and then AQA past paper questions. Make sure you've got answers available. I hope you feel you've benefited from the lesson. Please like or subscribe if you are so inclined. Please recommend to a friend if you think it would be helpful to them.